Okay, so I'll be following up from where Shubha has left, slightly different. So this will be talking about the structure of dark matter halos, which we think we understand very well, but we'll be talking about how these structures or the distribution of these structures of the shape parameters evolve with time, and there'll be a lot of universal functions. So this is being the first part of the talk will be with Ayan, who is the PhD student, and these guys. And the second part and the third part of the talks will involve these hydro simulations, which we have heard about. So I'll probably stop maybe in part 2, and if time permits, I'll go to part 3. So during my PhD, Sriram was on the panel. So he used to always ask, "What happens? Why are you not including baryons?" So I think we have heard a lot of talks where baryons do affect dark matter, and I'll show a couple of plots for Sriram there. Okay, so this is no baryons. This is just dark matter halos. This is a 10 to the 14 halo from a dark matter simulation, and this is with two halo finders. This is with SubFind and this is with Rockstar. And then we remove out all the satellites or the substructures, and you are left with these two halos, which we call the central halo. So we'll be talking about only central halos because satellites may affect the way we measure the shapes of these halos. So this is another such 10 to the 14 solar mass halo, very different in shape. And what we'll be doing again is to quantify the shapes and look at the distribution over the entire simulation, the distribution function of these shapes. So why shapes? Because what's plotted here is the halo mass function, and what has been done here is that you have, let's look at the pressure vector, which is the blue line. The data is from simulation, and this is what you call the ellipsoidal collapse, that is the Shed-Thorman mass function. We'll not look at talk about the Zeldovich related result. And you see that the simulations agree very well with the ellipsoidal collapse model. Okay. So look at the bias. Again, bias is also affected by whether we consider halos to be spherical or we consider them to be ellipsoidal. Okay, so this is just the definition of the mass function. On the left hand side, this is what we count. It's a histogram, and we just map it to this function. Is what is plotted here. There is a definition of nu being 1 over sigma square, or nu being 1 over sigma, which is different from what Ravi uses and what generally we use. Okay, but they are the same. So we have seen that simulation suggests that mass functions are better dealt with when you are analytically dealt with when you consider ellipsoidal collapse model. And what's done here is we have listed a few of these mass functions which are universal in nature. And here is one hydro simulation, massive black 1 and massive black 2, and it goes all the way to high redshifts. Okay, and the pressure vector doesn't do a good job. That's the key point here. But if I look at all the dark matter fitting functions that you look at, that you have used, these lie here, and with the hydro, this is consistently down. So at smaller masses, so this is like a mass scale, which has a redshift folded in. So the mass function is universal. It goes from right to left on the curve. Okay, and at lower masses, the hydro simulations are showing, at least this one is showing, that the abundances are suppressed consistently with whatever has been done in the literature. Okay, so it's important for looking at abundances in the context of shapes. Okay, there are some other things which I have listed out where the halo shapes are important and why one should start quantifying them a little more carefully. So looking, we have talked about clustering, 3-point function is something, and since bias is degenerate with the growing mode and sigma 8, it will affect again cosmology. Then what is the effect of baryons on halo shapes and vice versa, and how do halo shapes affect galaxy formation? So earlier halos, how do they compare with late time halos, and that will sort of dictate how galaxy grow in these halos. Okay, and then we have heard a lot of talk about dark matter interactions, and these typically may be affecting the inner profiles of halos. We have heard Shubha's talk about the velocity and the spatial structure. We also have velocity shapes, but we don't know how to interpret them, so I'm not going to talk about them right now. And then there is this nature versus nurture debate. Okay, so quick definition: we take our code, the n-body code or a hydro code. We take our favorite halo finder with subhalos, a subhalo finder. We define a 3 cross 3 shape tensor. Here xi and xj are particles I and j in the halo whose distances are with respect to the center. You have to come up with a definition of a center. And w is a weight. It can be taken to be unity or it can be weighted with respect to the radius. Okay. So you diagonalize this 3 cross 3 matrix, which is symmetric, and then you'll get the eigenvalues and the eigenvectors. The eigenvalues are the three axes, which you will talk about in the context of triaxial halos, and the eigenvectors are these directions. Okay. So one thing which we'll talk about a lot is the triaxiality parameter. So we are not interested in the absolute values of the axes, which are A, B, C ordered, but rather their ratios. And this is known as the triaxiality parameter. And basically it will determine whether an object is oblate, triaxial or prolate. Okay. Okay. So we'll use a bunch of scale-free runs. We'll also use a bunch of lambda CDM runs. So these are the range of indices for scale-free runs, and the reason we use that is to look for self-similarity, because scale-free runs are self-similar. So we have to make sure that our simulations are doing fine. So pretty large or reasonably large runs, okay, and we go out depending on the index as to the maximum. So this is like a RNL. RNL is the scale at which sigma at that scale becomes order unity. So just the classification, this is an oblate halo. T is from 0 to 1/3, and if A is of order B and is greater than C, so it's basically like a pancake or a UFO. Okay. So this is basically the random orientation in the simulation, and here we have aligned the largest axis along the z-axis. Okay. This is triaxial. It looks slightly different. Okay. And the three axes are ordered, and the triaxiality parameter is 1/3 to 2/3. And this is the prolate. Prolate is like a cigar, and you'll see this is like the face-on view of that, and this is the edge-on view. Okay. So this is another halo, which is prolate halo. Okay. So now what we do is to compute the shapes. We look at the Q and S, which are the ratios of B by A and C by A. And look at their distributions, and what has been plotted is as a function at every output that we have used. This is, let's just look at these two. These two are for Rockstar, these two are for Subfind. They look similar, so we can just for the time being ignore the half of the plots. Okay, this is for n is equal to 1, minus 1.3 and minus 1.5. And we are plotting the median of these distributions, okay, as a function of either m by m nonlinear or nu. Nu is in the y-axis, okay, and you see that it's a tight evolution, and it goes along some characteristic curve which we are going to quantify. Go to even more negative indices, minus 1.8, minus 2 and minus 2.2. Again, you see that the curve starts flattening both in Q and S. Okay, so the question is, do these curves fall on a single universal curve? And we have done this separately for the three types: O, T, P, O being oblate, T being triaxial, P being prolate, which are denoted as orange, blue and green. Okay. So again, you see for the different halo types, a characteristic curve along which these distributions or the medians of these distributions evolve. Okay, you put them together. This is for again minus 1.8 to minus 2 and 2.2, and then you see something similar. Now you put them together, and you see that there is a very tight relation for all the halos for across power spectra, okay, or the power law indices, and this is all those data combined together, and we are fitted just tan hyperbolic function on this. Okay. And you see the same thing or a similar thing, that you have universal curves separately for uh, the different halo types. Okay. So we are not sure what's happening, why it has to be universal, but we can invoke some self-similar behavior and get with that. The reason is that the self-similarity should hold for different ends, but it seems to hold across all ends. Okay, that's the universal part of it. So go to lambda CDM. I'm not going to show all those detailed plots, just the final plots. We have a bunch of runs, okay, and ranging from 75 MPC to GPC. And again, for all the halos, you start seeing something universal, and across halo types, again you see something similar. There are certain some differences here, but we think there's a finite volume effect which is hitting us for the smaller volumes, and these are the larger volumes. So this is what we have been seeing in these simulations, that the distribution follows a universal curve, and it goes from right to left. That's the evolution part. Okay. The next thing that we can see from here is that if I look at a particular mass at a certain redshift, and I ask the question, what does the mass look at a later redshift? Okay, because the new value will decrease with increasing for fixed mass, it will go on this direction. Okay, the mass becomes a little more rounder. Okay, or the shape becomes the object becomes more round at fixed mass. So that's something which one can infer from here. So let's look at mass functions. This is the full mass function. This is mass function by oblate, triaxial, and prolate. And again, you see something universal happening there. Okay, reasonably universal. And what you see here, the oblate fractions are small. They increase with time. Triaxial fractions are much little smaller, but not as small as this. But they also increase with time, and the prolate fraction decreases with time, again on one single curve. Okay. And in the QS space, you can start looking at these distributions, and you start off from here, which is yellow, redshift 3, this is lambda CDM, and you start moving along this trajectory. So that's the statement that typically halos become rounder at or more spherical at with evolution. Okay. So this is just a short summary and questions that one would like to address in the future. Okay. So what determines the shape of halos? Is it local environment cosmology? And what we have not done is to track individual halos through their history. So that is something which will be interesting to look at. And something which I think would be interesting is to look at these rare halos, which are the oblate halos, and how galaxies form, or are they very different when you look at these halos. Okay. So I'll quickly, now I think I have a 1 minute, 2 minutes. Okay. So I'll move to the second part and basically start looking at a multiple expansion of these halos. We'll just expand them with YLMs. Okay. So there is a radial part and there is an angular part. Okay. And we will look at the angular profile. This is what we are going to do. And then we cannot do rho 1, rho 2, rho 3, but we can take the mod square of rho, okay, because of the inner product. And we can look at the radial part of this anisotropic profile. Okay. So this is again an oblate halo. This is what we'll call L is equal to 1, we'll call the dipole, monopole, and quadrupole. Okay. So we are monopole is boring, we are not going to, it's just one color. So we are looking at dipole, and dipole is telling us that this is scaled with the monopole. So this is before rotation, this is after rotation. So this is what it looked in a dark matter only simulation. Okay, and you can see that the dipole term is weak, and basically it's telling us that it's pretty much triaxial. There is no deviation from triaxiality. We'll see another example where there will be a deviation. Okay, this is in the hydro. Okay, and you'll see that actually the T value has increased, so it has become slightly more spherical. This is for a triaxial halo. Okay, again these are with 100,000 particles, 10 to the 13 in lambda CDM, and notice again the dipole part, and then suddenly the dipole has come in hydro. And you can see there is some sort of anisotropy, might be baryonic effects, or it can be just the halo finder doing something. Okay. And finally, the prolate halo, again very low this thing, so it's like perfect ellipsoids. Okay, and then you have again the quadruple term. So let's just go back and stare at the quadruple part after alignment. Okay, you'll start seeing that they get sharper based on what the orientation have chosen. Okay, so this is one way. Another way of identifying which halo is oblate, prolate, or triaxial. The second message that we want to take from here is that the dipole term, we have a bunch of halos and most of them have dipole terms which are 0 or very small. Okay, which means that another way of quantifying is that these halos are nearly perfect triaxial halos. Okay, there are no distortions in their triaxiality. You can invert this question and ask the other question is that one can start using this to start picking out satellites. Okay, we have only expanded up to second order. Okay, you can put in third order, remove, you can put fourth order and remove, and identify satellites both in angular coordinates and if you want in radial coordinates. So this is 3 halos. This is the monopole, this is the quadrupole, the dot dashed, and this is the dipole. Right? So dipole again in radial terms it is small, and the differences. So this is with respect to rho total. So most of it, like 80-90% of the halos profile, is sort of determined by just 2 or 3 modes. Okay, so that's the message here. So I'm done, right? Okay.
Thank you. Questions?
So in the first part of your talk, so just like people worked out, universality of the halo mass function,
This is
the initial delta you can think of as sum of 3,
yes.
lambda 1 plus lambda 2 plus
Right.
lambda 3, those will be related to the shapes.
Yes.
Can you similarly work out, like the mass function you showed for individual, yeah, exactly. Is it possible to work this out?
One can start asking questions about the barrier for these 3 kind of halos and do the excursion set for them.
Have you looked into it?
No, we just. The second thing that you should notice is that this is the residual. This is between the Schett-Tormen and whatever is our fit is the largest. But Schett-Tormen does a decent job. It's not too bad.
Thank you for the very nice talk. So when you were discussing about these different multiple moments for halo as a function of radius, can you also look at SIDM halos with this, look into their internal structures, whether there is
so this has been integrated out to R. You can do radial thing also, right?
But there is a plot with as a function of radius, right? At the very end of your
you are integrating over a solid angle, meaning over the entire theta phi. So one part is integrating over R and finding out what it is over solid angle, right? So this is the R part, that is the rho LMs, and the other one is integrating over solid angle, okay, and then finding it as a function of R, but we can do it as a function of R also, this one, right? You can integrate up to R.
Up to a certain R.
Up to R.
Yes.
Right. Pardon? Yes. So we have done that and it changes. So suddenly a dipole will appear and then go away. So that we had shown, I think, in
Yeah,
previous
so I was wondering if you can do that exercise for SIDM.
SIDM is some interacting dark matter.
Yeah, self-interacting dark.
Self-interacting, okay. Yes, sure, you can do.
Okay, thank you.
You were looking at the triaxiality that a fixed nu. The fixed peak height. So I was wondering what happens if you actually start splitting the halos on the accretion rates or accretion histories, and if essentially maybe this universality is telling you how mergers evolve.
Right, right. So that's the, yes. So we have not looked at this part, right? So that's something harder. So this is just to take a snapshot and do it. But yeah, one has to compute what is the accretion rate and even the merger history, those kind of things. You can do that.
Yeah, because maybe that's what's setting
Probably. Yes.
like how halos.
Yeah. Yeah.
Okay. Yeah.
So under what will they go through cycles of OTP or not? That we don't know, right?
The next talk, I guess. Yeah.
Really, I don't know if I missed. Does your halo have substructure? Did you
Has,
talk about
but-
the alignments?
Pardon?
Did you talk about their alignment?
Yes, yes. But substructures, we have removed the substructures. We are only looking at centrals. So all, yeah.
Let's thank Nishi again.